Hey, we are MNOJS, and we did our project on Geoffrey Taylor's analysis of the action of waving cylindrical tails and propelling microscopic organisms. Taylor's paper is an investigation into propulsion in the media where viscous forces dominate. Due to the low Reynolds number environment, non-reciprocal motion is used as propulsion. The work done in this paper is especially relevant in microbiology and the design of biomedical devices of a microscopic scale. All macroscopic swimming animals, including fishes and humans, perform reciprocal motion to move through the fluid by generating enough forward momentum through inertial forces. However, this motion does not work in viscous environments since it generates forward and backward momentum that cancel each other out. As you can see in this video, the tail of the fish replica swings left to right. There is no net momentum that can move the object through the viscous fluid, even though it is the same movement as shown before. In low Reynolds number regimes, an irreciprocal motion, such as the movement of a body in the helical shape, can generate forward momentum. This is because viscous forces are high enough to propel the body through the fluid and inertia does not play a significant role. We replicated the latter phenomena. The paper by G.I. Taylor describes how swimming mechanisms between inertial and viscous environments differ and the relationships between coil parameters, final velocity, and torque. For validation, we also consulted a paper entitled Propulsions of Microorganisms by a Helical Flagellum by Chen et al. We will compare our quantitative results with the published values. While the visual on the left guided our understanding of Taylor's report, we chose to focus on the 2012 paper and its physical model, shown on the right, as it more succinctly describes these relationships in accordance with the slender body theory. The most important parameters were length, L, coil radius, A, wavelength, lambda, and amplitude, r. Our experimental setup consisted of a cantilever beam that had a stepper motor at its end. This stepper motor held a helical coil inside a viscous fluid. We aimed to measure the deflection of this beam as the fluid exerted a force on the coil. Our first iteration had a strain gauge to measure the deflection, but we ultimately decided to use a laser and a mirror to have a more granular and less noisy measurement. As you can see, we made use of a mirror attached to the top of the stepper motor to reflect the laser beam onto a grid paper on the ceiling. This allowed us to change the throw of the laser until we could have measurements at all ranges of motion of the beam. The swimming movement that we imitate is on a larger scale, so we have to increase the viscosity of the fluid. We ultimately chose honey because of its availability, transparency, and high viscosity value. If you look closely, you can see the beam moving as the force drives it upwards. In this video, you can see the green laser beam reflecting on the mirror and shining on the ceiling. We took the amplitude of this movement to calculate the force due to the constantly moving origin. The oscillation you see is due to the boundary conditions. We didn't want to buy 40 liters of honey, so we obviously are affected by the outside of the beaker. In regard to the second paper we showed in the beginning of the presentation, we found another paper done in 2012 that did a similar experiment to our problem. Here is a comparison of the setups. Our experiment used honey with a helical coil of 4 cm in diameter, and the paper used silicone oil with a helical coil of 1.28 cm in diameter. We calculated the viscosity of the honey by dropping a metal ball into the liquid and timing the fall. The Reynolds numbers of the two setups are not exactly the same, but we are still in the region where we should expect similar behavior. The paper stated that microorganisms driven by a helical flagellum are generally in an environment where the Reynolds number is from 10 to the negative 2 to 10 to the negative 4. As we just saw in the video, the rotation of the helical coil produces a thrust force in the honey. The force results in the oscillation motion of the steel beam, which is measurable by our laser setup. By reading the laser displacement, we were able to calculate the thrust force. This is a graph of the thrust force over time at different RPMs. As we can see in the graph, as we increase RPM, the period of the oscillation motion decreases, and the amplitude increases, which should be intuitive. We did experiments with 6 different RPMs, but for you to better understand our data, let's just look at 3 of them together. So here, at 10 RPM, the amplitude is about 90. At 20, the amplitude is about 150, and at 40, the amplitude is about 230.
However, besides a change of amplitude, there is also a change of offset. If we zoom in on the y-axis, we can see that not all of the curves start at 0.
Here we've zoomed in time, and we see that the offset of the oscillation increases as RPM increases too. This change is very small and doesn't align with the order of magnitude of the thrust force we're expecting, so we decided to ignore it. We have some guesses about why there is an oscillation with this tiny offset, but we can discuss it after this project. Right now, we're just going to use the amplitude as the magnitude of our thrust force. We collected data on 2 days. First day, we ran the experiment 3 times, and on the second day, 4 times. We are pretty happy with the consistency of the data, so let's move forward to the data analysis. The paper included a graph of force relative to rotation rate and showed that there is a linear relationship and that the force is 0 when rotation rate is 0. And here is our data. As we mentioned before, our experiment has a different Reynolds number from the one in the paper. Specifically, the viscosity of the fluid and the diameter of the coil are very different. So we normalized our force by dividing it by mu and r squared, which gives us a dimensionless variable.
As you can see, our data is pretty close to the data from the paper. The yellow dashed line is a linear best fit line to our results. At 0.5 Hz, the paper data read around 3 and ours read around 3.5.
However, our best fit line doesn't intercept at the origin. When rotation rate is 0, force should be 0. In addition, our curve seems to be steeper when the rotation rate is low, and falter when the rate is high, so our data is not perfectly linear.
So there are several things in our setup that might introduce error. First is that because our beaker is only 3 or 4 times wider than our coil, boundary condition has an effect on the motion, which we didn't consider. The second thing is that the steel beam is mounted on the tank with a 3D printed piece. We assume that the deflection of the beam is linear to the thrust force it sees, but possible deformation of the 3D printed part might introduce errors. Thirdly, the motor has a mass and weighs down the beam, causing the helix to be at an angle within the beaker, unevenly interacting with the sides.
Here we've zoomed in time, and we see that Damn, I'm so popular!
Here we have zoomed in time, and we see that the offset of the oscillation increase at the RPM increases too. Shit.
The paper included a graph of force relative to rotation rate and showed that there is a linear relationship. Stop!